So, welcome to YouTube, right? Welcome to YouTube. I think I have done a lot recently, but just try to code some shit because I have been pissed off by this this BTree. So if you want to watch this stream, just watch it. Right? I'm just coding, and if you have questions, you can just ask me. I think I should be able to see the comments, right? Whatever, just coding. Yeah. So just realize it's possible to use a proxy to get to stream on the YouTube because we know that China is censored the internet, right? Whatever, just do some coding. I mean, to be honest, I'm just fighting the fucking computing freedom for the computing freedom for entire my day. I'm super tired. You know, it's just coding, and I have no idea what's how to piss off because I just write a string BTree. The BTree is just as a template for me to implement further stuff because this is just for something that is just for further stuff, right? Yeah. Okay, let's just do the coding. Wow, 3 people are watching now, right? There's three people are watching. I think I'm being super lazy doing this streaming now. I think I should just lower the quality of the video. I think whether I'm a bot now. Yeah, I think I should be able to just press the video and do this, right? Whatever, nobody's gonna watch. I think nobody's gonna watch. It's good. This is so sad. This BTree just destroys me because I really have no idea how to write this at all. So difficult. It's so bullshit that C doesn't have a BTree, right? And even if it does, it still sucks. Just C standard containers are bad. They are bad, right? They're just bad from every perspective. It's 30 degrees Celsius. What is here is doing shit? Hey, no, please, no. I really. Whoa. Just send them signals like saying you're gonna stop it or something. What is the situation here? I think this is the simplest situation. Is the simplest case is to move all the data for the BTree to move the string forward. That's one of it. Parent equals nor. We're gonna delete the nor. Delete the root, right? What else? Let me see. Where can I guess install a console to see your stuff? Cursor. What is the cursor? Jack shit. It's been several weeks now. I have forgot what I wrote at all completely. I'm gonna sometime now print some data out. Hold shift. Yeah, I did hold the shift. Why? It's so ugly. This should be better. Oh, I just cannot see anything. Is it working on without? Oh no, it doesn't support web PWA version of GitHub Copilot. Why the fuck? Let's just try to. Let's just try remove Apple, okay? Let's just try remove Apple. Wait. If it tries to remove the leftmost, then I cannot just do this, right? Because that the root will get destroyed. I just realized that. There's just one case. Let me think. Nope. It won't break it because it will recall the leftmost of the BTree node. We are not destroying the leftmost entire node. We just destroy the node, one element in that node. Even if the leftmost, it's still the same location. Just for the beginning, it won't break it. I don't think it can break it. So let's just try. Let me try. See whether I can open the console and put a console here. We can see the console here. The terminal command. Let me see whether I can put the terminal here and put it here. Put it somewhere. So we can see the terminal. Now let's just put it here and put it smaller and put it somewhere here. Okay, this should work. Let me check whether this work fine. Should measure 130. Yep, looks like it works, but no, it's still way too small. Let me check it. Maybe I need to put a font here bigger. Can I make this shit bigger? No, it's even smaller now. So we cannot do this. I cannot do this. I'm 200%. This should work now. Yep. This is great. So we can also. Wow! It's way too big. It's way too big. I think we need to. Wow, this is cool. This is super big. I enjoy it. I enjoy this. Okay, let's just go back to coding here. I just gonna stop here to save them some traffic. Please, using this to play the music. What is import is doing here? Is it just a pointer, or it tries to record the leftmost node and the rightmost nodes too?你说。What? It's not finding the SDR BTree. Oh. Maybe for some reason I did. What? $647. $375. What? Why did I put those here? Yeah. In 85. $385. Oh yeah. Dialog pointer 405. ITV 405. ITV 1. An L value of this. Initialize parameter type with a type. Okay. It didn't really matter. We really don't need to freaking care about the node type. Node type is pretty useless. Just useless. Well, it's still useful. Yeah, it's still useful. Yeah. This should work. I'm trying to. Min 2. OVC. Is that anything here? IOVC. Min 2. 2 IOVC. What is this type for? IOV base then base is called base and then okay. And we shouldn't do this. Should static cast. Oh, still need. I think I have changed the title here. Yeah. I think I really need to get rid of this thing here. Because they're really useless. They are just useless. Well, adding template below. Let's just first do it first, okay. Void const star. Assigning from const to void star const. Just too many consts, just bullshit. I hate const. There was a reason why C does not have const. Because it is literally just grammar noise. Well, it adds nothing to optimization. It adds nothing. Parent. Please, no more const, okay? No more const. Then we do a static cast. Just get rid of this fucking C++ type system, okay? So it's A now, right? Let's just try back, then just try erase banana. Do we have banana? Okay, banana. I think banana should be the second one, right? Banana. Yeah, banana. That's the cherry. We'll just do it one by one to see what's going on. Banana. Cold dumped. Free cold dumped. 440, then it starts to, it needs to split, and when it splits it just becomes round now. We basically need to use the medias everywhere. What is the node doing here? So here's node. Node tries to find another node. Yeah. So this part need probably also need, I don't know. This pointer conversion thing is just annoying. I really want to get rid of the entire junk here. Just make a pointer. I don't give a fuck about. Let's just make it. Voice star. Is that a node? I think it's node. Node, yeah. Node. That's pulse, right? So now we can get rid of a node type here, just leave it a key number. It's called a comment. Shit. Single template sucks. It really sucks. Let's just get rid of doing this later on. Okay, not doing here. Nobody's willing to deal with the trouble here. Why? Now we are entering this part. To Genie Planner, we need to go the left side. Move the node, move all the node here, and then do this stuff. So we have nodes in half. After that, we should recursively go above it. First to check with the node. This is so annoying. BTree is the most frustrated data structure I have with it. I'm just frustrated with it. Hey, where's my pen? Where's my pen? This is the machine. The power. The power left. Batteries. No more battery. Why? Is this pen broken or something? On the pen here. Yeah. Connect Wi-Fi. Yes, okay. Really fuck security. Fuck security people. Fuck security. Please. It's the right mouse we can do. No, not the reason. What's gonna do if you have the rightmost of the node? You have one tree at the bottom, at the top, and 3 nodes. Let's assume 2 nodes, 2 keys here. And then we will have 3 children, right? They would have also 3 nodes. Assume that we have 3 of them, both true. If we're gonna remove the rightmost, what are you gonna do? Should we just go back to tell the rightmost or something? Because we should always try to borrow node from the right. But who is gonna borrow it for the right itself? It cannot be the leftmost, right? No. Let me ask Copilot. Let me ask AI. This mouse and keyboard is just so bad. I hate it. Yep. The keyboard not working anymore. I hate it. This, when the mouse works, the keyboard doesn't work. When both of them don't. So what hell is going on? Just terrible mouse and keyboard. Finally get it work. Let's just go here back. I think we should borrow the left, right? For example, if I ask a Copilot, what's it gonna do if I have we try to in 7, what is going to happen? I'm asking this question. I'm going to remove, right, with 4 nodes. Seven is in the tree, right? You want to remove 7. What are you going to do? You want 8, right? So five, order 5. So if we are removing something from the rightmost of a node, we are borrowing from its left. We always borrow from the left, right? From the right, right? That question, crucial part of deletion. NT. So let's just first implement the first side. Is that we should try see whether we can borrow from the left or from the right. We shouldn't always try to just merge the code. We should just make it more balanced. So the tree should be so when we're doing this, we have to borrow from the left. The tree should become 3, 6, 1, 2. We should borrow it. Would you just borrow from the left? If we remove 7, for example, then we would do this, right? Then this would be a legal tree. We would first try to see if it's below that. We're gonna try the right side and then try the left side, right? To see whether we can borrow something. If we could, we first borrow it. If we couldn't, we're just gonna merge it, right? We're gonna merge with the left or merge with the right. What if we just try to put a number here? Well, that would be complicated. The deletion of BTree is so difficult. It's so hard. It's just hard. So, what is this? Let's just not do this again. Let's just do nothing. Let's just avoid this part. First, if we don't have enough nodes, right? So what we're gonna do is that we're gonna emulate it by trying to borrow, see whether we are in the leaf or not. Here's we are in the leaf, right? So we are in the leaf node. So in the leaf node, the thing is becoming much easier than it should. It's hard when we are not doing the leaf node. It's trying to pull something down. Let me think. Well, this is so complicated. BTree is so hard. No wonder people a lot of people don't like it. Despite it's super important, just people don't enjoy it. So we have the leaf. We try something on the right. Too hard. This is way too hard. We have the leaf. We don't have enough nodes. If we're not in enough nodes, then we should try to recursively remove the node here. Should we do it recursively or not doing recursively? Let's just not first do it recursively, because we should avoid recursive as much as possible if we can. If we can just avoid it, we just avoid it. We shouldn't care about it, right? I plus plus equals A. Key numbers half plus plus A. Should we do this? No, we shouldn't do this. We just merge it. We shouldn't just try to keep borrowing. We just try to first see its right side and see its left side, to see whether it has element or not. Okay, now we're gonna try whether it's left or the right. So who is the parent? Here's the parent, right? Parent, we have parent is, we know our node. Do we know it? I think we should. We should know what is our pose is. A parent pose is. Children's, right? So we're gonna try the parent or parent side, right? Parents in or something. Parent size. And next we're gonna try the pupils to see whether pupils is the number. Well, yeah, whether pupils is the parent side. If it's not, we're gonna try first borrow from its left, right? Because we should borrow it from this left. Then we'll try the the left child, right? The brother, left brother. Left brother. And then we try the right brother. But what if could that happen? No, it's not going to happen because let me think more. No, it's not going to happen because the parent would always have at least one node. Because if it doesn't have at least one node, we won't be able to see anything, right? I don't know whether it has the property of saying what's the property of BTree. So BTree's definition not here. The successor up. Move the successor up. So what's the definition of BTree? Does the root set? Oh yeah. So it says besides the root node, we must have at least k nodes, right? So the root node can have one, but even it does have one, it shouldn't be a problem. So we're gonna at most do it twice, right? So if we try to remove something from the node, let's assume we did it, then it's equal to doing a rotation and then doing the remove the leaf node. So the most important part is to remove the leaf node here and trying to find the successor and move the node here and then try to delete it or merge it, whatever you call it. Can be even more complicated, like if we try to remove something from the center. But even it is removed from the center, it's actually equals to, after rotation, is equals to remove from the bottom, right? Because that's what's going to happen. So if we're going to remove the node here, we're going to first test whether it's the right side. If it is the right side, we will try to borrow it from the right first to see whether we can borrow it from the right. So we try the right sibling. Right brother. Our right brother is node. Oh, we can cross pointer, but I'm not going to pass pointer here. I think we can cross the pointer. What is it causing undefined behavior if we just try to do it here? If it is full, that actually is not, right? Because casting pointer doesn't cause undefined behavior. So we can actually do this by just static cast for the pointer here, but static cast to here, to the keys number, and then doing the auto here. With auto here, we're gonna cast the pointer. The pointer, can we just give it an alias type here? Okay, shall we? Don't give it too much pointer. Give it just called set common node, right? Node pointer. Okay, I think node pointer should be okay. Node pointer. So what we're gonna do is parent our children and then we're gonna do a parent size purpose, right? Parent size purpose we're gonna do purpose. We're gonna cast the purpose +1, right? Can we dereference it? No, we may not be able to dereference it, because if we are on the right side, what's gonna happen is that if we try to find 5, it's not have 5. So if it is not have 5, then it is problem. So we're gonna doing a here or something like this. And then if it is that case, we're gonna try the right brother equals here, right? Equals here. And we're gonna try to see whether right brother's size is equals to is smaller than keys half, right? So if it is, then if the children is right brother n keys number half is smaller than equal than right brother n, then so if right brother n is larger, we can just borrow it. If it is smaller, we couldn't borrow it, right? We cannot borrow the node here. So we're gonna first try to borrow it, which means if after we borrow it, we're gonna return it, because we can borrow the node here. So we're gonna borrow from right sibling. Can we just borrow it? Probably not, because let me check. If it just borrows something from the right, and it happens to say we try to borrow from the right, from the right. But if we borrow this part, we actually should borrow is the successor. So sibling is the successor, right brother's leftmost node, right? So we're gonna keep going down, wow, that becomes complicated here, right? Because if we just borrow the node here, we may break the tree, right? We can break the property of the tree. I think that's the case, right? So we may just break the property of the tree by doing so. So that's an issue, right? 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8. Right, what's gonna happen if we try to, let's assume there's something. 6, 7, 8, 9, 10, and then we have 4, 5 here. 4, 5. Now we have 7, 4, 5. Let's just try here's 9. 7, 8. 9, 10, 10, 11. 12, 13, and 14, right? If we try to remove 2 from the tree, what's going to happen? Why is it so complicated, to be honest? I think what our problem is something like 1, 2, 4, 5, right? That it's not 5. It's something like 6. Here we have 3 and 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10, 11, right? It could happen because it doesn't break the property of the tree. Here is a tree. Here is right. Here's how the trees looks like. Trees looks like something like this. So I have a tree. I try to remove 2 for a 5 or 5 BTree. Oh, the root allows 4 nodes, right? No, we remove 2. but now 5 is not correct, right? So the AI is talking shit now. You go by the but no. It's the property. The tree, right? How we handle this? How do we handle this? One, three. Gosh, there's no way I can do anything. 4, 3 down. It violates the rule. So we're gonna fix it. We're gonna fix with the rule 1. We're gonna fix with the rule 1. Right. What the AI says. The AI says, let's just go here. Let me show you the screen here. OBS. Show you the screen of the of AI. So the Microsoft Copilot. Okay. So the AI says, if we try to remove the tree here, we have a tree like this, okay? This is the BTree. If we remove 2, it's gonna break the property of the tree, right? Because now this node only have 1, and it violates a rule because it's non-root key. It's a non-root leaf, right? Now we need to borrow something from other node here. So but if we just remove 3 and borrow for the right successor, it's gonna break the property of tree again because now 5 is only one number. So what we can do next? I think the it's like removing 4 from the node. So we're gonna break it again, but it looks like too complicated. So it breaks the tree. So the AI is talking shit. It actually breaking the tree. So what is gonna do? What are you gonna do? We're gonna remove 2, borrow 4 from 5, and now we have 5. So 5 is invalid. What are we going to fix it? Now it put it toward. How could 12 become twice? No, this doesn't make sense, right? This doesn't make sense. The AI is talking shit. Okay, let's just try it. Maybe we need 6, 9. How could it become 6, 9? But 6 doesn't have nodes now, right? So if we try to remove 2, the tree becomes 1. It's underflows. Try to borrow from Cyberlink. how could it become this? How does this magic work? So we promote 6, 9 to be the new root. We can promote the entire root to be a root. What? Okay, if we remove 3, we remove 2. So now we don't have root. Because if we remove 2, 3 is going to go down. And now we don't have root anymore. Well, this part becomes super complicated, right? It's really hard to think about it. Let me ask other people, right? I have a tree like this. What's going to happen? It's way too hard. Data structure. Do you have data structure Discord? Discord. The algorithms. I must leave a server to enter this server. Okay. Sounds like too many servers here. Oh, maybe, what is this doing? Let's just quit it. Leave the server. Discussion. A BTree. what is going to happen? Algorithm. Whatever, JavaScript, C and C++, whatever. Who can teach me this? Introduction to algorithm. The introduction to algorithm explains all the possibility here. Introduction to algorithm. Here's a PDF note. What is deletion here? Nobody knows. It looks like delete the key from the node. What? BTree delete. Write pseudocode for BTree delete. Fibonacci here. Oh, Fibonacci key could make something to be order 1, right? What is Fibonacci key? I forgot it. I forgot all the algorithm here. Fibonacci. What is Fibonacci here? What? Delete mean that cache friendly. Pointer structures. Decrease here and update key operations. Shines one decrease heap. The standards pop flow. It's amortized heap. Fibonacci priority queue, right? Fibonacci heap. Wow, that's. I forgot this guy. Fibonacci heap, right? Fucking Fibonacci heap. Just so many things to learn. Way too hard. Union decrease heap. That's Dextra. Fibonacci heap. Double linked list. Anywhere secure double linked list in order 1, and you can calculate them into one circular here. Yeah, the double linked list in order 1. Minimum. Let's see. Fibonacci. Priority queue. What is Fibonacci even doing here? really F the people who wrote the introduction to algorithm, who created all these stupid algorithms. Right? These data structures are just awful. Way worse than they should. My question is, how can you delete, not insert, delete something from the BTree? Right? It's hard to do things like this. Okay, let's just try to see the deletion. I'm seeing deletion. If we try to delete key K in node X, then we delete K. If we delete F, and then if we try to delete F, if we try to delete F, we delete F. The G. Please kill me. It's so painful. The BTree deletion is so painful, you know. It's gonna be BTree. How is it gonna work? Let me see whether we can watch some video on talking about how BTree deletion. We should be able to see that, right? BTree deletion. Let's just watch some India videos on this, right? Maybe India is gonna tell us how it is. Maybe, okay. Let's watch a video, right? BTree deletion. Yeah, let's just watch a video. Do you think this woman is gonna explain it well, or this guy? I won't get lost in the matter. I think this guy is probably can do a lot of job. Oh, how it work? Hmm. 21. Okay. Huh? Why is not 25? Oh, because it doesn't have that. What? What? Why? Why? Wait, did you 17? Why would you do this? What? 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 Something like this is great. If we did it 17, why would it break the property? It needs to do something. Is it just trying to remove 22 or because of that? its recursion path have. Loading recursion path, we have T-bonus 1 key. Doesn't make sense, right? Because we're at 70. Why? I think maybe I got something wrong here. BTree is way too hard. Way too hard. Then why? It doesn't make sense. It doesn't break tree, any property of the tree, right? If we remove 17. I don't think this, it looks like something wrong here. Let's just try to see what Indian women say. So, see, the BTree is so complicated. One deletion would take 28 minutes for these women to explain, right? Yeah, that makes sense, right?
So for example, we are going to delete, suppose 64. You are asked to delete 64. Now first thing is you are supposed to search where is 64. Now searching would be from there, root node only. 64 is greater than 50, less than 80. So, we will go to this path. 64 is greater than 60. So, right to the 60, less than 70. So, here we will go this part. Here we got what? 64. Now, you check. This target key is in the leaf node, plus this leaf node contains more than minimum number of keys. Minimum number of keys are 2 and this contains 3 keys. So, this is the simplest case. What you have to do? You just simply delete the 64. After deleting 64, how many keys are there in this node? 2. So, it is still having the property of B tree, because any node in this B tree can contain minimum 2 keys. Okay. Now, this is the simplest case. No need to do anything, just delete that key, target key. Second situation is if the target key is in the leaf node and that leaf node contains minimum number of keys. Okay. Let us take one example. We are going to delete 23. Now, locate where is 23, less than 50. Here this side greater than 10, greater than 20. So, this side here we go to what? 23. But you cannot simply delete this 23. Why? So, because if you delete this one, then the remaining key in this node is only 1. And that will violate the property of B tree, because what B tree says, any node, every node contains minimum number of keys, how many? 2, except root node. Root node can contain 1 key. Okay. So, now in this case what you have to do, this case is there, that leaf node contains minimum number of keys, minimum number of keys are 2. Now, here 3 possibilities can be there. Fine. Now, this key, this node can borrow key from its, either from its immediate left node or from its immediate right node. See, I am saying immediate left, immediate right. Okay. Now, see, first case is, suppose borrow from immediate left node, or you can say sibling. Here you will refer this sibling. Okay. So, in this case, obviously we don't have any right sibling, so we will go to the left sibling. Left sibling is this. This node will ask, I want to borrow 1 key, can you give me? Now, the situation is, this node will say yes. Why so? Because this node contains more than minimum number of keys. So, here the situation is, it can borrow any key from its immediate siblings if and only if that sibling is having more than minimum number of keys. So, here this left sibling is having more than minimum number of keys. So, yes, it can borrow key, but it cannot directly borrow key from here to here. Okay. The rule is, the key would be borrowed through the parent node. So, the procedure is what? Here we are borrowing key from the left sibling. So, what happens? From this node, the maximum value would be transferred to its parent node. Maximum value is what? 16. and say this value of this parent node would be transferred to here, to this node. After that we will delete what, 23. Okay, so this is the procedure. Now I am going to update in this case only. Now see why we have taken this 16. If you take this 15, if you write here 15, so in that case here is 14 and 16, but that is violating the property of BST also, because this is a BST tree na. So to the left of 15 we cannot put 16, because to the left of 15 only values less than 15 can be there. That is why we take the maximum value from the left sibling. So this is the first case. Now second case may be, a situation can be like that left sibling is not having more than minimum number of keys, so it will check with its right sibling. Suppose if right sibling is having, just immediate right node is having more than minimum number of keys, then borrow key from the right sibling. Let us take one case. Suppose we are going to delete what, 72. Now see, first of all locate where is 72. Searching would be from here, 50 greater than 50 less than 80 this side, 72 is greater than 70 this side and less than 75. So here we go to what, 72. So this is a leaf node. That leaf node contains only minimum number of keys, so it has to borrow something from left or right sibling. Left sibling is not having more than minimum number of keys. Here right sibling is having only, here we go search. Now same would be from here, 50 greater than 50 less than 80 this side, 72 is greater than 70 this side and less than 75. So here we go to what, 72. So this is a leaf node. That leaf node contains only minimum number of keys, so it has to borrow something from left or right sibling. Left sibling is not having more than minimum number of keys. Here right sibling is having more than minimum number of keys, so it will borrow key from its immediate right node. How this thing will happen? Through the parent node. Now here if we are borrowing a key from the right sibling, then from that node the minimum value would be transferred to root node. So minimum value of this is 77. 77 would be transferred from here to here, and now 75 would be transferred to here only, and then we delete what, 72. And here also 73 would be this side, 75 would be this side, because it is a BST, binary search tree. So I am going to update here only. I hope you are getting this concept. Okay, so this is this case. Now third case may be if neither left sibling nor right sibling is having more than minimum number of keys, then what will happen? See, now suppose you want to delete now 65. Now locate where is 65. 65 is greater than 50 less than 80 this side, greater than 60 less than 70 this side. Here we got 65. You cannot delete directly 65 because this node is having minimum number of keys, not more than minimum number of keys. So minimum number of keys, then this situation can be there. Immediate left, it will ask to it immediate left check. No, it cannot give one key because it is having only minimum number of keys. Immediate right is this key. This also cannot give one key to this node because this is also having minimum number of keys. Now the third case arises. Now what will happen? If this situation is there, neither we can take from left nor we can take from right sibling, then we are going to merge this node with either its left sibling or its right sibling. Okay, plus parent node would also be merged. How this thing would happen? Suppose I am going to merge this one with this left sibling. So after merging this one, what the scenario is, 51, 52, here we have 65, here we have 68. See, suppose directly we have merged this one, but this is not the case. This is not how you do it. You have to add parent also in this net. And which parent key you will add? We are merging this one and this one. So the parent between these nodes it's 60, right? So this 60 would also be merged with this case, with here. So 60 would be 51, 52, here we write 60, here 65, 68. Fine. From here you will delete this 60 and after that you will delete what, 65. because obviously here we have 5 keys, that is not possible, maximum number of keys can be 4. So after merging this, because we are going to delete this 65, so after merging this node with this left sibling, the situation is the tree is something like this. See, this would be same, this would be same, this would be same, only the change is here only. So I have just written this change. We will also merge, we will also add this parent node in this merge, this parent node. Why? So because we are merging this one and this one, so the in between parent of this merging node will be added. So in between is 60, so we will add 60 here. So we will delete 60 from here, so remaining is 70 and 77, and here we will merge this one 51, 52, then 60 is here, 65 would be deleted, and then 68. This one, this is to the left of 70, to the right of 70 we have 73, 75, to the right of 77 we have 78 and 79. Or you can merge this node with this also. There the scenario would be something like this. If you are merging this one and this one, then in between parent of this node is 70, then 70 would be merged with this, with these one. So the situation 60, even 20, this one. This tree is satisfying the B. After the case, here on the tree would be something like this, and this tree is satisfying the BTree properties. So now suppose you are deleting 20. How to delete 20? Find out where 20 is. To the left of 50, to the right of 60 is 16. Here we have 20. But that it is in leaf node, but that leaf node is having only minimum number of keys. You cannot directly delete it. Okay. Now this node will ask, can borrow key from either from its immediate left node or immediate right node. There is no immediate right, so immediate left. But this node cannot give one key to this node. Why so? Because this node is also having only minimum number of keys. Now what will happen? So it will ask to the parent node that I cannot borrow any node from my siblings node. So it will say that you have to come down now, you have to do something. Now what parent node will do? This parent will come down and merge these two siblings. Now the situation is something like this. Everything would be same. Here only change is 10. Only 10 is there. To the left of 10 we are having 4, 5 and 6. And we will merge this one. This 14, then 15, then 16 would be come down. The parent would become here only, then 20 and 27. After that you will delete this 20. Okay. This is the case now. This would be the case. But that is not done. We are not done with this deleting of this 20. Why so? Because see, after deleting this 20, now this node is having only one key, and that is violating the property of BTree. Every node must have 2 minimum number of keys except root node. For now I am going to update this change here only. Okay. Now here only one key is there. We are not done with deletion of this 20 because here only one key is there, and that is not possible in BTree. So now this node will ask to its sibling, no left sibling, so it will ask to it right sibling, can you give me one key? No, cannot give one key to this because why? This node is having only minimum number of keys. Now what will happen? Now it will go to its parent node. Now parent node will have to do something. Now parent node will do what? Parent node will come down and will merge this and this one, and the situation is something like this. When 50 will come down, then the root would be only 80. To the left of 80 we have this 10, then we have 50. This would be merged with this one 70 and 77. To the right of 80 this part would be same. Now what about these children? To the left of 10 we have 4, 5, 6, 4, 5, 6. Right of 10 and left of 50 we have these children 14, 15, 16 and 27. To the right of 50 we have what? 50 has come down. So right of 50 are this one. We have merged this also. To the right of 15 would be 50 would be 51, 52, 60 and 68. Same right of 70, write down as it is. Right of 70 are 73 and 75, and right of 77 are 78 and 79. And to the right of 80 this part would be as it is. So this is how after deletion of this 20, the tree is going to be rearranged. See, arranging of these children would be very easy because we are following the property of BST. So, for any node to the left of that node, all the keys would be less than that node, and to the right of that node, all the keys would be greater than that node. All the keys in the right subtree would be greater than that node. Okay. So, I am going to update this thing here only. So, now we will discuss the second possibility. If the target key is in the internal node. Okay. Now, see, here also 3 sub cases are there. Node only. So, now we will discuss the second possibility. If the target key is in the internal node. Okay. Now, see, here also 3 sub cases are there. See, internal node means that node contains its left side also and right child also. So, you can take either in order predecessor or in order successor, as we have discussed in deletion in binary search tree. Okay. Now, so B, the maximum element from its left subtree. So, 70 के left में क्या है? This one. In order, this the minimum key, the minimum element from its right subtree. So, to the right of 95 we have this one. So, minimum key from this is 100. So, this is in order successor, and this node which contains in order successor is having more than minimum number of keys. So, we can replace this target key with in order successor. This is the second case. Okay. Now, we will delete this 95 and we will replace 95 with this in order successor. In order successor is 100. We will delete this 100 from here. Here remaining are 2, that is fine because minimum can be 2. Now, suppose you want to delete 77. Where is 77? To the left of 80? Here. Here is 77 in the internal node. Now, check out. In order predecessor is here 75. But we cannot take 75 because this node contains only minimum number of keys. Check out for in order successor. In order successor of this is 78, but we cannot take 78 because this node also contains minimum number of keys. So, now if this situation is there, then we are going to merge this one with this one, that is 73, 75 and also with 77, then 78, 79, and then we will delete 77. So, only 4 nodes are there. From here also we will delete 77. So, the remaining node in this are 10, 50 and 68. To the right of 68 we are having this node. Okay. 73, 75 and we are going to merge this one 78 and 79 and we are going to delete this 77 from here. So, this is the case now. So, this is the third case how we are going to solve this one. Now, suppose you want to delete 80, it is here. You can either replace it with in order predecessor. Check out what is in order predecessor of 80. To the left subtree of 80 is this one. So, in order predecessor would be the maximum element from the left subtree. Maximum element is 79. So, see this in order predecessor, this node is containing more than minimum number of keys. So, we can replace this 80 with 79. So, this is the situation after deleting 80. Now, suppose you want to delete 100. Now, what is the case? See, where is 100? This side, to the right of 70, to the right of 90. Here we have 100. Now, check out. In order predecessor is 93, but we cannot replace with this because this node is having only minimum number of keys. In order successor is 110, but we cannot replace with this one because this is also having minimum number of keys. Now, the third option was merge these two with this one. Now, the situation is something like that. This here, this is same. To the right side here we have 90, to the left of 98. This node can you minimum? Okay. Now, if you are borrowing from the left sibling, then the max parent node. So 68 would be transferred. Okay. Now if you are borrowing from the left sibling, then the maximum would be more than minimum number of keys. Now which this will give key through the parent node. Okay. Now if you are borrowing from the left sibling, then the maximum key would be transferred to its root node, to its parent node, sorry. So 68 would be transferred here, here 68 would be transferred, and 79 would be transferred to this side. Okay. So now if 68 has been transferred, so these elements, the right of 68, obviously these elements would also be transferred to the right side, na? Because these are to the right of 68. Now the situation is something like this. Here you will write what? 68, 78 would be transferred here. So 78 would be to the left of 90, 79 would be left of 90, fine. Now if 68 has been transferred here, so the right of 68 element would also be transferred. So these elements would be to the right of 68 but to the left of 79 node. So this node is having left child also and right child also. So you can you give me, but the sibling is also having now in this video we will see how to delete data from BTree. We will discuss all the cases of deletion, right? The order of this tree is 4. So index, you can say from 5 here, because see the value here, no, because
We are discussing how to do the insertion and deletion operation on a B plus tree. So we know that in case of insertion and
so we will try to borrow the element from the right sibling, sorry, left sibling. We will try to borrow the element from the left sibling. So how I can borrow, whether I have to check before borrowing it, can it able to give it to me or not, we have to check. It means can I borrow it or not. If it gives one element from me, it will have only, already it is having 3. If it gives to me, it is 2. 2 keys in a node is allowed because minimum is 2, so it is allowed. So this left sibling is in a position to give me one element.
My question is about the leaf. If I try to delete something and the leaf, is it left side or right side? So in my happen is the leaf is the node is the leaf for sure, but is left browser and is right browser are not leaves. Could that be the case? Is that possible? I think that's possible, right? So if that's the case, I'm trying to delete the here node here. It won't be able to merge with it because the left side isn't a leaf. Should I just do some rotation or doing something? Or maybe in the insertion part is guaranteed that it won't happen. Let me ask the AI, okay? I think we need to ask the AI now. So, the question, is that possible for a B tree that its siblings, its brothers, itself, that the node itself is a leaf. Itself is a leaf, but its brothers are not. But it, what would happen if I delete 25? Right? But it breaks property, right? If I try to borrow something here, let me draw the graph here, okay? I think I should first draw the graph, then later on put the numbers there. Right? because the root we don't care. No, please, no. Yeah. I don't think it's just trying to explain it well. I'm trying to draw the graph, but I couldn't. Can delete the graph. Okay, just redraw it. Can't do anything. That's insane. 这个华为的变那个。嘿嘿。Now, how could they borrow? You cannot borrow anything, right? Because if you just put on a 15, you have no nodes, right? If you just put on 15, you have no nodes. Okay, that's it. Just today starts streaming. I'm stuck with it. I don't think any of these AI is providing the right correct explanation here.